All right, what's going on, everybody? Today we're going to be doing another LeetCode video. This one is called Validate Binary Search Tree. So we're basically given the root of a binary tree, and they want us to determine if it's a valid binary search tree. If it's valid, we can return true, and if it's invalid, we'll return false. Okay, so that's pretty straightforward, but what is a valid binary search tree? Well, let's just look at the exact definition here, just to get that out of the way. So the left subtree of a node can only have values that are less than the parent node's value. And then the right subtree can only contain nodes with values that are greater than that parent node's value. Okay. Also, those left and right subtrees have to have the same property all the way down the tree. So it's got to recursively be valid all the way down to the leaf nodes. So let's look at some input-output examples, just the ones LeetCode gives us. So this binary search tree is pretty easy to validate because there's only 3 nodes. So we really just need to check, okay, this left subtree does it have nodes that are all less than this 2? Yes. Same for the right subtree, but the inverse. So all of the nodes in the right subtree have values that are greater than that 2. So it's a valid binary search tree. We just return true. So from the next example, we can see while this left child node, this left subtree does have nodes that are all less than this 5. This right child node immediately has a value that's less than this 5 when it should be all of the values in the subtree should be greater than 5. So this is going to be an invalid binary search tree, and obviously the output for that is false. So let's go ahead and start whiteboarding this. So right away, we need to, the way I would think about this problem, it is a binary tree problem, so I'd probably go for some kind of recursive solution, just for, an elegant, just for elegant code. And it's always usually pretty efficient. Sometimes there can be constant space iterative solutions, but nevertheless, we're going to go for a recursive solution here. So maybe a depth first search. And when designing an algorithm, you have to think of a way to basically determine if at each node, if each node basically adheres to the policy of a valid binary search tree when you're looking at it. So one thing you might think to do, and I'll show why this is wrong, is pretty much say, okay, is this node, for every node, is this node between its left and right child nodes? You can't do that at all because, let's say we had a binary search tree that was like, have like a 5 here, maybe a 1 there, 10, and then like a 2. So this wouldn't be a valid binary search tree with even if we did those conditions I just discussed. So like if we looked at this 5 and said, okay, is it between its left and right children? Yes. We could, 1 doesn't have any children, 10 does have children. Okay, is it between its left and right children? Yes, but obviously this isn't a valid binary search tree, right? Because this right subtree has a node that's less than this parent node here. So that's a violation. All of the nodes, remember, in this right subtree need to be greater than this 5. So how do we account for that? Well, in each recursive call, we need to pass in basically a current minimum and maximum, because basically as you go down the tree, there's like less and less options that you can have. Like you're going to have a decreasing basically window of possible numbers. So for example, like going down this tree, so all of the nodes in this subtree would have to be greater than 5, right? But think about when you go this way. Now all of a sudden they have to be, not only do they have to be, and that's incorrect, wait a second, that's less than 5, greater than 5. So they all have to be greater than 5, but not only do they have to be greater than 5, if we went left, now all of a sudden they also have to be less than 10, right? To keep that property true. So we're gonna have to have a min and a max at each recursive call to be able to accurately validate each node. So So the way I'm going to do that is I'll keep track of the min with blue and then the current max with red. So let's go ahead and step through the algorithm for this tree here. So yeah, so we're just going to start. We're going to start traversing our tree. Our minimum at first will just be negative infinity, and then our maximum will be positive infinity. Okay, so we're gonna do recursive depth first search, and I'll call the left children first. So we're gonna go down this way, and we're basically gonna check, okay, well, first we need to check, okay, is 30 within those bounds? Yes, it is. So we return, well, we don't return anything yet. We're gonna do our recursive calls and return true at the very bottom of them. But we are gonna return false when if we find one that's invalid. So let me make one of these invalid actually, so we can see exactly what happens. So this 20, let's make that a 31. Okay, so we're at this node. So our new, we're gonna have a new maximum, right? Because we're traveling left. So there's like an invisible max wall here, sort of, whenever we travel left. So our new maximum is gonna be 30 for this subtree, and our minimum is gonna stay at negative infinity. Okay, so now we're gonna say, okay, is 15 between negative infinity and 30? Yes, it is. So we can keep doing recursion. So let's go this way. Again, we're going left, so we need to update that max value. That new max possible value is gonna be 15. And then our minimum value is gonna stay the same because we're going left. So now we're gonna check, okay, is this 10 between negative infinity and 15? Yes, it is. So at that point, we would go left, but there would be a null node. So once we get to a null pointer, we're basically just going to return true because we've gotten all the way to the bottom of the tree. And we can assume we've seen true up to that point. So now we're going to basically be going all the way back up. We're going to pop back up, but not that far, actually, because we can go right this way. So whenever we're going right, there's like an invisible wall here, once again, right, that we have to update our new minimum value. So our new minimum is going to be 15, and then the new maximum will be, let's see, it was 30. It doesn't change. Okay, but now we're going to check, okay, is this 31 between 15 and 30? Well, it's above 15, but it's below 30, so that's a violation. So we'd actually return false there. We'd return false, and basically that would bubble all the way back up to the top. And if we ever see false, this whole outer function is going to return false. Basically, we need to see true. We need to see true for every single null pointer to pop back up to the top as true to have a true valid binary search tree. But this is basically the in essence, the algorithm. It's pretty straightforward. So let's get into the code. And actually, right before we get into the code, let's talk about the space and time and space complexity. So our time complexity here is just going to be big O of n, where n is the total number of nodes in the tree, because we have to visit every single node exactly once, to determine if the entire tree is valid. And then the space complexity is just going to be big O of h on average. Average meaning depending on how the tree is skewed. If it's heavily skewed one direction, it could be closer to big O of n, but it's basically going to be big O of h for the number of levels in the tree for that recursive call stack. So it's going to be big O of h space. All right, so let's get into the code. So basically, the first thing we're going to want to do is write our recursive function, because we can literally just seed our recursive function here. So in our return value, right? Because we just care about whether this comes all the way back up to the top as true, or if it comes all the way back up to the top as false. So we're going to pass in that root node at first, and we're going to have a long max value, and actually this is just long min because that'll be our minimum for the given subtree we're at in our recursive call, and then this will be the maximum for the given subtree we're at in our recursive call. So long min, long max, and those need to be long because there are test cases for this problem in C++ where they give you absurdly big integers, so you have to use a long here to pass all the test cases on LeetCode. So that's why we're using long. You can try using regular integer values and it will fail. So, but anyways, yeah, we're gonna have a Boolean value for our depth first search, our recursive depth first search function. We're gonna have a tree node that I'll just, or a pointer to a tree node rather, that I'll just call tn, and then we're gonna have a long value for our minimum at the subtree we're in, and then a long value for the maximum at the subtree we're in. Okay, so for our function, basically first we're gonna check if our tree node is null pointer. If it is, then we can just return true because we can assume we've made it all the way down to basically all the way down to the null pointers that are directly underneath a leaf node, which would infer, that would tell us that everything we've seen to that point has been true, because there's always going to be at least one node in the tree. So we don't have to worry about a case where the root here is null. So anyways, once we get to a null node, we can assume everything's been true so far. So we're gonna just return true. Okay, then we need to check basically our condition, right? So if our tree node value is greater than, or this is gonna, we need to check basically if we're violating the rules we have set. So if tree node value is less than min, and really it should be or equal to, because we can't have duplicate nodes with duplicate values in a binary search tree. That's illegal. So anyways, yeah, tree node val less than or equal to min, and it has to be that value at the tree node we're at has to be greater than or equal to the max for this to be an invalid binary search tree. So we'd return false if either of those are true. And really that should be an or, right? Because we're just checking if either of those conditions are potentially violated, not both of them. So yeah, so that's what we do there to check that. And then basically what we need to do for a recursion is, it's kind of special, right? The way we update our min and max values depending on the direction we're traveling down the tree, or depending if we're going to the left child or the right child. So our depth first search, we're just going to call DFS, and well, actually this is going to be an if function, right? Because we want to check all of the subtrees recursively. So we'll do, it needs to be an and comparison on the depth first search because we want these to be true. So we're going to call depth first search on the left child and the right child, and we need both of those to be true, and then we'd return true if all of those are true. And then if they're not all true, we return false because we need to return something in all control paths, and catch if one of these starts returning false, pretty much. Or if we get a false return value anywhere in our binary tree. So first we're gonna call recursion on the left child, and this is actually tree node, right? So tree node left, and the way whenever we're traveling left, we need to update the maximum value for that left subtree, right, to be whatever the value is of the current value of the node we're on. So this will be min stays the same, and then max will just be tree node val. And then for the right child traversal, the max will get updated to the tree node val that we're on, and then, or the min will get updated to the tree node val we're on, and then the max will stay the same. So that's pretty much it for the code. So let's go ahead and run this, and make sure there aren't any bugs. So yeah, it looks good. Hopefully this video helped you understand the problem better. If it did, leave a like and subscribe, and I'll see you guys in the next piece.